Welcome. This is a talk by students who responded to a problem from our SCUDEM, which is a 3-student presentation and modeling activity. And they did exceptional work, and we've asked them to join us and tell us about their work and how they did it. When Kelly Black, who is the person who makes up these problems from us from the University of Georgia in Athens, Georgia, comes up with these problems each summer for the next fall, part of me goes, are you kidding me? I mean, how is anybody going to get a hold of anything to do this? And Kelly and I have this friendly discussion, and eventually we settle on the nature of the problem. And then lo and behold, folks like this from your program at Duquesne come up with marvelous ideas and solutions. And it's a joy to read them. And we have judges from around the world who judge them and usually give about 8 sets of comments and feedback. And we just rank them from top to bottom and have a cutoff line of outstanding through successful. And I'm so glad that you're willing to share that. So I will stop and turn it over to Kyla, Megan, and Mitchell. Thank you.
Thank you so much, Brian, for the wonderful introduction, and thank you to SIMIODE for having us here today. So I'm going to start us off by just introducing the problem and our team. So we chose problem A, which is sweet tooth and heavy metal. My name is Kyla Covato. My team members are Megan Kwiatkowski and Mitchell Livengood. We are all from Duquesne University in Pittsburgh, PA, and our mentor is Dr. Kimberly Williams. So just a little agenda real quick. We will be going over the preparations that we did before the SCUDEM challenge began, and then we'll dive into how we approached the problem and finish up with where we are now and our next steps. So in terms of preparations, we started by taking a look at previous outstanding videos to identify aspects that we liked and what we would do differently to improve. For example, we really liked the presentations with simple templates and well-organized slides. And then to improve, we wanted to personalize our presentation using a cameo function of PowerPoint. So we put our little faces in the video that we made. And then after reviewing the previous videos, we then shifted our focus towards a few basic models. Primarily, we've used the ODE solvers and MATLAB to practice the predator-prey model and the compartment model. And our team has exposure to differential equations in the past, but it took a significant effort to actually learn these new modeling techniques. So we met with Dr. Williams at least once a week to ensure that we would have the capabilities to independently work through a problem during the actual challenge period. So this is just a practice problem that follows the logistic model, and it models the percent of married women since 1920. So this is one of our practice ones. And then here's another practice problem, which follows the compartment model and models homelessness based on multiple variables. For this one, we practice solving with least squares approximation and if statements. And then we also utilize that built-in ODE solver, again, all in MATLAB. So the competition period, when it started, we reviewed each problem individually and then came together to decide on problem A, which is entitled Sweet Tooth and Heavy Metal. So the main objective here is to construct a model that will help researchers track the long-term dynamics associated with heavy metal levels in a person who consumes contaminated chocolate. And we initially started by planning our model using the compartment model that we looked at earlier, where the chocolate came into the body from the environment and then was excreted. We found constants such as the half-lives of metal in the blood, as well as constants like the amount of metal per serving of chocolate. So then after settling into the compartment model, we found supporting data that allowed us to calculate the excretion rates, and then we made our equations from there. We determined the necessary parameters and then started making a bunch of assumptions to kind of simplify the equations. So we assumed that our person that we were modeling for was a healthy American child with a typical diet. And the problem wanted us to specifically look into children for accumulation effects and consider birthdays and holiday effects on chocolate consumption. So to simplify that, we assumed that chocolate eating habits stayed the same each year. And we found that chocolate sales data were directly proportional to the number of servings consumed per week of dark chocolate. But this data set was incomplete, so then we extrapolated the data and assumed that Easter and Halloween chocolate consumptions were identical. And a quick Google search showed us that Easter is just as big for chocolate sales and Halloween in the United States. Finally, we examined how a child's birthday can affect the accumulation, as a child who might have a birthday near a big holiday like Easter or Halloween. And for this, we assumed a 10% increase in chocolate consumption during the 13-week period that the birthday fell. We then did this because we expected a child to get a lot of chocolate around their birthday and ultimately eat it over time, not all at once. So for our final consumptions, we in terms of like metal considerations, there's not a lot of data on blood half-lives of heavy metals for children. So we assumed that the half-life is the same for a child and an adult. We also assumed that the only source of heavy metals that came from polluted dark chocolate, and we set all other sources to 0. So that would include milk chocolate and white chocolate. We considered this as an addition to the metals already in there from other sources like meat and fish. And finally, we assumed that a constant amount of heavy metal is in each serving, and that helped to simplify our assumptions. So I'm going to pass it over to Mitchell.
Hello. So once we had made our assumptions, we needed some data to project with. So we needed to find intake rates and output rates. We assumed that the contaminants would follow a decay model, so we needed to find those decay rates. We needed to find intake rates, so the amount of contaminants in a serving, and we had to find some variability because you're not going to eat the exact same amount of chocolate every day for your entire life, so we needed to find some way to model that. The contaminant amounts was the easiest part to find. That was provided in the problem statement. It highlights the differences in the levels of metal in the mean, median, and at minimum and maximum, various different ways. We examined all of these cases because they were provided, so we figured that that would be one of the best ways to answer the problem. So we used all of them. After using that, we had to figure out how fast it would leave the body. So we found blood half-lives of heavy metals. Blood has some differences than bone, and so we kind of just ignored that and assumed that it would be constant. We do want to explore it further in the future and take into account the bone holding onto it and the blood processing it a little bit faster. And we will probably be exploring that soon, but for this short-term project period, we just went with a constant of 25 years for lead, 14.2 years for cadmium, 20 hours for arsenic, and arsenic is really fast, which did cause us a problem that I will point out in a couple slides. So to use those decay constants, we used that simple amount of contaminant remaining is equal to the initial amount times e to the negative lambda t, where that lambda is the decay constant. And once you set n and n naught equal to 1 and 2, you can calculate lambda from the half-life. To find chocolate intake, we found this amazing graph from statista.com, which showed yearly candy sales on a weekly basis. It looked promising, but it was based on sales in millions, and it did not contain Easter data, which is kind of important because Easter has a lot of chocolate rabbits and chocolate eggs and things like that. So we thought that that would be important. So I took that data and pulled it from Halloween back to Easter and assumed that Halloween and Easter would have similar amounts of consumption. So it's a little bit bigger here. You can see up at the peak, it's 1,101 million US dollars. So we just divided this by the median value, and that got it from about 0.4 to 1.2, I believe. So we had to fill the rest, which I just used Excel to do that. So you can now see that peak that's in around Easter and the peak that's around Halloween have the exact same shape. So we pasted it back, and then once we put it into MATLAB from that Excel file, we had to normalize it. So we multiplied it by 7 days a week, 3.14 grams per serving, and then divided by 30 grams per serving. And then we divided it by the median to make it normal. We then had to figure out how to get it from discrete points into something that the ODE solver could use. So we had been learning about Fourier series in signals and systems, and I said, hey, this would fit this problem pretty well. So I turned around and went into the MATLAB curve fitting suite. And at first I went for a 1-term or 2-term, and then thought to myself, we're not doing this by hand. Go for 8. You don't have to do the math. So we went all the way to 8, and you can see all of the coefficients there. And it ended up fitting the graph pretty well. We visually made sure that it looked correct. It misses a couple points. The spikes at Valentine's Day and Easter aren't filled out completely, but most people aren't going to eat that massive amount of chocolate. So it does help to smooth the data out a little bit. We could have checked it with the least squares type of checking or some other accuracy checker like that, but we already had introduced error and we were on a time crunch, so just checked it visually. Once we got that, we considered this shape of problem where the amount of contaminant in or out is equal to that Fourier variability function times the amount of contaminant coming in minus the amount that's there times the decay constant. But you can see that the arsenic was so fast to leave that it started ticking into the negatives. And because the body will never have a negative amount, we tossed this one out and went for a simpler one that did not introduce error. So this is the one we ended up with, where the amount of contaminant coming in or out is equal to the variability function, that Fourier servings approximation, times the amount of contaminant coming in, times e to the negative lambda t. And that did it for each of them. And you can see on that graph that it's not going negative, and we like that a lot better. Now I'm going to pass it on to Megan so she can talk about her part.
Okay. So our next steps were, once we created our equations, we worked on exploring the effects of different concentrations of heavy metals in the chocolate, and we created the corresponding figures for analysis. And it allowed us to examine the bioaccumulation of the heavy metals in these varied situations from that table before. The biggest challenge for us with this was finding a concise way to present a lot of the data we had in a very effective manner. This is the table from before. In this presentation, we're focusing on the median and the California Prop 65 limit, as they best show the effects of the varying the heavy metal concentrations per serving. This chart shows the wide variations found in that Hands et al. Paper that was referenced. We found there was quite the effect on the bioaccumulation when varying the concentrations. And when we change those concentrations, we're changing the PBN, the CDN, or the ASN term in our equation. The California Proposition 65 requires our businesses and companies to provide a warning for significant chemical exposure that can cause cancer or other harm within the body. The Prop 65 maximum allowable doses for lead, cadmium, arsenic were 0.5 micrograms per day, 4.1 micrograms per day, and 10 micrograms per day, respectively. As part of our project, we looked at the bioaccumulation of these heavy metals over a 1-year period as well as over a lifetime. So we looked at about 80 years. the cadmium levels rose to a very concerning amount when compared to this lead and arsenic, and even the arsenic rose much higher than it had with the other situations, as we'll see. And then this model kind of confirms that these heavy metal levels are concerning for long-term accumulation and consumption. And then these figures show the lead, cadmium, and arsenic accumulation over 1 year and 80 years with that median concentration from the table. For all the situations we explored, we noticed this similar shape in the graph over the short term and the long term. It was just where it leveled out in the concentration that changed between the differences, but we got a similar shape overall. And then this graph shows the bioaccumulation of the cadmium during each birthday period. So this was the final part of the problem where we assumed a 10% increase in each 13-week period. And this is to account for all the children getting a lot of chocolate and eating it in controlled amounts, not eating all of it all at once. The birthday period that coincide with the major holidays like Valentine's Day, Easter, Halloween, and Christmas see a much higher bioaccumulation than those birthdays in the summer months, which is the yellow curve where you don't see as high of an accumulation. Overall, our model found that the cadmium accumulated at much higher rates than lead or arsenic, and then the lead and cadmium levels could be concerning over time, leading to long-term health effects. On the other hand, arsenic was quickly processed by the body and in reasonable doses, didn't really seem concerning at this time. And then the medium concentrations of the heavy metals found in the paper is less than the defined maximum allowable dose from Prop 65, so not much to worry about there. While we were making our model, we came across some improvements that we considered, but we just didn't have the time to explore fully. So some of those were dark versus milk chocolate. The paper focused only on dark chocolate. So we were considering, oh, what if long-term, how does dark chocolate versus milk chocolate vary? Male versus female, as we have different excretion rates for certain materials. Other heavy metals like mercury, we also considered exploring. As well as we considered exploring the effects of the age of the individual. So we looked at children here. Children versus adult was something we could explore. And then diet changes, either with consuming more servings per week or cutting out chocolate completely. With our improvements and our alternate models kind of in mind, we weren't quite done after the competition. After the competition period, we sat down and re-examined the previous models we had explored, and using the feedback from the judges and consulting with our mentor, we are working on modifying our model to include the long-term excretion for metals staying in the blood as well as the urinary excretion rates. We noticed with our model that there were some issues in our thinking. One example was if the child stopped eating chocolate, we would expect the concentrations to fall to 0 over time, yet our model failed to account for that change. So we knew something needed to be changed. This is an updated graph with the subtracted term to account for excretion that Mitchell talked about earlier. It varies from the one earlier, as arsenic no longer falls to 0 though, or falls below 0. It's making it a little bit more realistic of a model. We definitely still have a lot of work to do in refining and updating our equations to best represent the excretion of metal from the body. Here are some of our resources. And then thank you guys so much for the opportunity to compete in this challenge. And thank you everyone for being here today. And with that, are there any questions?
Wow, thank you very, very much.